setting it to share. Okay, well, thank you for continuing to show up. I'm just learning how to stage this thing. Continue to show up. This Wednesday, I suggest that everyone comes to the lab at Wednesday evening at 5. If your schedule allows, if you cannot come in person, try to log in. I think it will be kind of crash course session so that we pick up whatever was forgotten before. And I'll check if we can do presentations this Friday. Maybe it is a little too ambitious, but very soon we need to do presentations and go to use of the MATLAB skills rather than learning them, because basically those are everything one can read from help. We just make sure that you guys will teach each other. We are in the course of physical chemistry, setting a goal to describe properties of molecules and materials by understanding their principles and converting concepts into mathematical equations and solving them. This is the way. In this big journal, we are focusing on wavy nature of electron, and currently we are solving simplest possible problem. The universe where there are no molecules, there are no atoms, there is only this one electron. And we did set up a scientific question. If we prepare the electron localized in a certain area and give it average momentum, what would it do this time? The hypothesis was that average momentum will stay. The center of the packet will move same as classical particle, but the localization width will expand, right? And we are suffering some long mathematical procedures to get through it. If you have completed homework 2, please send it to me. If you haven't, please send it to me by Wednesday morning class. The credit will stay with you, but if you are submitting it right now, you are getting bigger credit. So what I'm going to do is to show. Also, if you are on the online mode and there are questions, you are very welcome to type, but voice is preferred so that I know where to look at what you are doing. So a little bit notes on the homework. So those who have submitted. Well, I'll give some notes. If you already completed, it will be like as a guides to check whether you did it correctly. If you haven't, it will help you to do it later. I'm not disclosing all solution, but showing the navigating through process. So for Fourier expansion, since the function is periodic, we focus only on one period. And we need to convert a function of x into discrete set of numbers. So we need to find a sub n and b sub n for number smaller than 6. So it is discrete, this is a set of discrete numbers. And the definition of Fourier transform, that you take a function, multiply it by cosine, and here the number n, here and the number n, there is the same. And for sine part, just replace function, but it is the same and here and there. Integrals from minus infinity to plus infinity for periodic functions will give infinity from scratch, right? So it's not as interesting. So when it would be quite correct to look on the range of one period. So we multiply this function by cosine, full cosine, half cosine, and for each frequency of cosine we get different discrete number. Now practically how we do it? We integrate from 0 to L, but it is important that our function f is either 0 or 1, right? And it is 0 in the range from half period from L over 2 to the L. So we can chop the integral on two ranges from 0 to L over 2 and from L over 2 to L, and the second part will be 0. So basically, instead of going from minus infinity to plus infinity, we integrate from 0 to L over 2. Okay. And if we set up, scroll it back. If we set up the frequency parameter here, this k, if you set up k equals 0, what is the cosine of 0?
1.
Correct? So we do the first term, k naught equals integral from 0 to L over 2. Then our function equals 1. It doesn't, so our function equals 1 in this limit, and the cosine equals 1 in this limit, right? So it's dx. So what is the integral of dx?
X.
Okay, so you get x changing from 0 to L over 2, which means L over 2 minus 0. So, and from the definition of the Fourier transform, and it is my shortcoming, I didn't announce and provide a definition, so if you forget it, you will not get withdrawn credit. One needs to normalize in this way, dividing by the size of the simulation cell. So with this definition, the V naught is 1 over L times L over 2, which will be 1/2. So the meaning of this constant is that the interesting. I learn something new every day. So if our function changes as a step between 0 and 1, then the average level is 1/2. So A naught shows 1/2 of this, shows the average level of this function. But then to give you a chance to do something if you haven't submitted it yet. So for all indices bigger than 0, coefficient in front of cosine is expected to be 0, and for B, for sine coefficients, there should be symmetry. So with odd numbers, it should be 0, and with even, it should be some function of n, which let me try to find. Okay. So problem number 2 is just copy pasting from the lecture notes, and the answer for the number 3 is expansion coefficient to what we are doing in class, converting the past of the wave function into set of discrete coefficients. And we expect to get square root pi sigma parameter, where sigma is width. And then there will be exponential, which is again negative squared, and sigma naught parameter is not in the denominator but in the numerator. And I will check if there is a 1/4 factor for the whole power. So I'll take some time talking more about it. Let me check how you guys did those who submitted. Well, some steps are skipped, so it's good for getting full credit, but I cannot judge whether it was really solved. So I'll better provide some ideas. And I hate exams, and I hope neither you will request it nor I will be in the mood. But just in case, if this class would be followed by written exams with problems, this problem would be very appropriate. So it's some material that you may want to cover. So how do we get this exponential as function of k squared? I'll tell it anyway. So I'll announce what we do in the class, but basically the first noticeable part of the class will be again this integral, because for this chapter it is an important part. So when I hope to leave the class after showing this slide once again, and let me provide interpretation and focus on the answer, so that if you really do not want to follow what is going on during the lecture, you can at least take this take-home message. So I'll probably do a little staging. Goes this way. Okay. Our main question was how that width of the wave packet changes in time with time. And the hypothesis was that it expands. Today, through the homework, which we already know the answer, the meaning of the homework that in the, no, I cannot say this. Don't worry, I have a clear thought what to do, just finding the right words. So we did started a journey into auxiliary abstract world, where it's only one electron. But in this world, the space is like Cartesian positions, right? Position, which in like in our real space. But we also can imagine space of momentum. Like if we analyze cars on the road, then in the space of momentum, it will be like from 0 to whatever is maximal 200 mph. And there will be a distribution with majority near like 60. And there will be some slow moving, some quickly moving, but it will be some distribution. So it is a profile of cars on the linear space of highway projected onto momentum space. Make sense? The answer to problem 3 in your homework, my homework, our homework, is projection of this localized wave packet onto momentum space, because our basis functions are plane waves for each plane wave momentum is well defined, and we check with which velocities, which momenta are contribute to the wave packet. And the Gaussian shape that is correct answer for the question 3 homework 2 is distribution of the velocities in momentum space. So it's our probabilistic particle, but it has distribution of velocities, which means it with some probability it moves quicker, with another probability it moves slower, with another probability it moves backwards. So it is main principle how we compose from basis functions the actual stuff. And the answer in homework 2 problem 3 does not depend on time. And even if you do everything in a very advanced fashion, it will not depend. So shape distribution in momentum space for this poor particle will be the same. So it will be not time dependent. But after we complete all exercises for today's class, we will get the distribution of the spatial localization of the particle in our real Cartesian position space. And we will discover that it expands. Make sense? I should keep it as a surprise, but we will see the surprise. And now there is a little crazy idea. What if we combine, if you take these profiles and measure their width, basically how fat is wave function in space of real positions and in space of momentum. And just for curiosity, we multiply these two width parameters. So it is what is shown on the slide. So sigma x is width, is how fat it is in the position space. Sigma sub p is how fat it is in the momentum space. And as a result of today's discussion, you will see the product of these two fat parameters always increase as time goes forward in time. So product of this width in position and momentum always increases. And this is a signature of one fundamental property of quantum theory that we didn't cover in your presentations. So that, and it formulates as, so width means it is not certain. It can be this and there, right? So with narrow widths, it is certain. With big widths, it is uncertain. And product of these width parameters is product of two uncertainties. And the statement is uncertainties of position and momentum for any particle is increasing. It's always bigger than some threshold, which is on the lower equation, sigma x, sigma p, bigger than h bar square over 2. And even so, no matter what happens, the product of these two things cannot be smaller than this threshold, Planck constant squared. And philosophical interpretation of this, that if you live in the quantum world, then one cannot simultaneously find position and momentum of a particle with arbitrary precision. It will be always uncertainty. If you know for sure where it is, then it will be with uncertain velocity. If you know for sure what velocity is, then we will not know where it is. Like certain velocity is plane wave, which is distributed everywhere. Certain position is a Gaussian wave function, which we can make very narrow, but then it is contributed from all velocities. So please try to write it down in your own words, because I cannot do better than I already tried. Check if there are any questions on the chat line. No. Check. It's connected. So if you are on the online mode also, you may want to practice this little exercise and write down your vision of the uncertainty principle. It's better if you try it now, because now you have fresh minds, not contaminated with mathematical equations in a big extent. So if you just share your impression with yourself later on, it could be helpful. Everyone finished. So what did you get?
We don't know the speed, but we know where it is. If we don't know where it is, we know the speed. And I wrote speed is Gaussian, placement is plane.
Okay. What did you
I said we can know where a particle is or the velocity, but we can never know both at the same time.
Okay. Yep. Makes sense. So let's go into more details of this stuff, and I really want to give some suggestions on the integral for the whole of it as we go through. So, assuming that homework answer is already known, we practice this progression from past to the future, and we need to take this integral. Last time we agreed to rename parts of this long equation and combine product of three exponentials as one exponential with summation of the arguments. And it is what we are looking at right now. So if we need to take this Gaussian integral, there is a trick. And I would be happy to write it from scratch. I just like it as a little poem. It's very fun math. So we need to take integral from minus to plus infinity of a Gaussian function e to the minus x squared. So instead of breaking my head and trying to solve it, I wasn't able to solve this integral. I've got a hint from my instructor when I was in the undergraduate times. So let's assume that we find two of such integrals, one along x and another along y. And then we will process product of these integrals, which should be equal. And then if we find these integrals and then take square root, it will be what we need. Make sense? Now, let's use geometrical argument. If we combine two exponentials into one exponential with summation, it will be e to the power minus x squared plus y squared, which is radius, distance from center, right? So, and then since it is two integrals, it will be dx dy. What is dx dy? Is a little area element, right? So geometrically, we do have the distance from center, and then this dx dy area element. So basically, we as a function, we have Gaussian, which depends only as distance from center, and then we integrate it over space, so two-dimensional integral. Over. There is a symmetry in this problem, because the contribution of element does depend on distance, but does not depend on angle, right? On one hand. On another hand, there is always a chance to convert from the rectangular coordinates to polar coordinates. there is nothing wrong. Then distance is x squared plus y squared square root, and angle is like cosine is x divided by radius, and sine is y divided by radius, right? One always can do like a Pythagorean theorem and find the angle as function of this x and y projections. How do we write down integral? So the function remains the same, and area element instead of dx dy, it will be r dr d phi. And the argument why it is this r dr d phi can be analyzed this way. If the area of the inside the circle is pr squared, then the derivative of the area over the radius is length of the arch. And if we make a derivative over the angle, it will be r. But now, if you want to just multiply left and right of this equation by increment of angle and increment of the radius, it will be increment of area is r dr d phi. Make sense? So here's how we come here. So it is the I squared, because it is integral over from 0 to infinity over radius, and from 0 to 2 pi over d phi, and then e to the minus radius squared r d, and here should be dr d phi, dr d phi. So the function does not depend on angle, therefore we take integral over the angle right away, and it will bring the integral of d phi from 0 to 2 pi, we will just give 2 pi, right? And then we have the remaining integral r dr e minus r squared. So this is something that I believe every one of us can do. So the elegant way to solve such integrals is change the integration variable. So what if we do not have this exponential? If you do not have this exponential, then it will be integral of r dr, which is r squared. Or we can consider it as integral of differential of r squared over 2. So why don't we use this trick and consider r squared over 2 or just r squared as new independent variable, and we'll call it with letter u. So if you do the substitution, then our integral will look like, and as a price for changing variable and 1/2, it comes up front here. So it will be integral of e to the minus u, so u is r squared, du, right? And it is the only type of integrals I want to actually take. The integral of exponential is exponential. And after we take this integral, we need just to roll over the whole sequence. So if we find it, I'm not writing it, but exponential to e to the minus u, integral will be e to the minus u. And then the limits are 0 and minus infinity. E to the minus infinity is 0, right? E to the power 0 is 1. So the answer is 1, and we have factor 1/2 up front. So it is And then we have 2 pi from the integration over angle. Then 2 pi times 1/2 will be pi. So I squared equals pi. And then I will be a square root of pi. Make sense? And then one needs to roll over all this chain of substitutions. So our actual, and right now I'm not focusing on homework. I'm primarily talking about the class material, which was to take this integral in the reverse direction. In homework, we are moving from position to momentum. We are finding this distribution in momentum space, and it is Gaussian integral. In class, we are predicting future, and we are going from momentum to position. But it is again a Gaussian integral. At home, we integrated over x. Now we are integrating over k. But mathematically, it is the same integral. So dk exponential minus ak squared dk. So if you do know how to take this Gaussian integrals, if you know that it will be square root of pi, we just need to convert this one into this shape. So we need to practice substitution of variables that will convert it into preferable form. What do? We identify full square in here. And if something is missing, we multiply and divide the whole thing on the missing factor. And just to play it easier, we'll consider this a k squared as square root of a squared times k squared. Then we can interpret the upper stuff as lower a squared plus 2ab, and then there is a missing third term, but we can add and subtract. Let me check if I'm going too quick with or too slow with those of us who are on the online. Any questions online? No questions? Please do not hesitate. Even if you just feel irritated or it is too quick, just give me the feedback. I'm telling the story not for myself, but hoping that you find it fun, maybe. Okay, going further. So, identifying full square. So this is lowercase a squared. Here we had only b times k, right? But we do want to identify like 2a lowercase b lowercase. So let's match it with our lowercase a by identifying this, multiplying and dividing by square root of a. Then this one will be a. This one will be b capital divided by square root of a will be b. And then we are missing whatever we define as b. Okay, so b capital divided by 2 square root of a. We can multiply by such exponential and then divide by such exponential. We'll put minus here. So we do not lie, we are mathematically correct. And we are getting this stuff, or better, we are getting a plus b squared. So this term, and this term come into full square. And this one does not depend on integration variable, so it is just a price for identifying full square exchange of variable. This one will be integrated, and this one will stay as a free term, and it will stay as a factor after finishing integration. Okay. So it is basically what we did. Full square, and here is a term that will stay as a factor of one. Now, the stuff here does depends on k, on the integration variable. And if you carefully, I believe I skipped some steps because time was up previous year and it is up this year as well. But if one carefully process this integral, one is getting our favorite e to the minus y squared dy. So I believe you can identify it if you need to reduce yourself. And this stuff stays as a factor. The 1 over square root of a comes when one carefully processes from here to there, from circle to square box. And c should be defined before, and this factor stays here. So which question I ask myself when I look here? On the left side I have x and t, and on the right I do not have x and t. And my goal was to predict future. So I should look for definitions of all these factors here and find where are x and t there. In the remaining 6 minutes. No, I think that the biggest skip was here. After that, things are go quite automatically. So, of course, it is my cheat sheet. If I would derive it right in front of you guys, I need a bigger blackboard and write important things on left side and then return and look for this definition. So I'm just bringing back stuff. So, when we were identifying full square for lowercase b, it was uppercase b over square root of a. And at the end of last lecture, at the beginning of this one, we set up b is imaginary unit times x, and the a was, while combining factors with, that depends on k linearly, we had one from initial condition and another from accumulation of phase. And if you combine them together, we are going to get something interesting. So we bring in these two things here. So it will be x in the denominator and square root of the time-dependent thing in the denominator. So if I carefully process it, then wave function of the future will be this blue stuff. So and I skip factors because they do not contribute anything to analysis. So it is exponential, which is Gaussian. It is minus x squared. Right? So you still have the Gaussian shape, and it is one of the answers to our original question. And in the denominator of this exponential, we will have the initial width, and factors here cancel for the denominator, plus imaginary unit, fundamental constants, times t. So on one hand, we can celebrate that we have found the first quantum problem in our life. We did predict the future of the electron in a free space. So we know the wave function of this system at any point of position and space. This is good. This is true celebration. But do we consider this equation pleasant or ugly?
Ugly?
I'm totally with you. Can we do any scientific analysis out of it?
Be very difficult.
Exactly. Almost impossible. especially drives me nuts the imaginary unit in the denominator of exponential. It's something crazy. It's not for humans. So we need to do something to bring this equation into pleasant form, or at least less adverse. So what is the strategy? What would be the pleasant form of this equation? I'm slowly learning your names, but I have already forgotten who was presenting what at the postulates. But one of the postulates was that if you know wave function, you can find probability distribution, right? So the main meaning of the wave function is if we need to take it absolute value square, and then it will be probability density to find the particle in certain region. Absolute value square, or wave function conjugated times wave function without conjugation. So no matter about technical details, but we need to square wave function to get something useful. So let's go ahead and make square of this blue stuff. Yeah, those are just technical details how we arrive. And if we, let me check if I was rushing and skipping details in last year. So if we take the blue wave function that we just discussed and make it square, or multiply wave function by its conjugation. Conjugation, one changes, flips the sign in front of imaginary unit, and when one carefully practices this multiplication, imaginary unit will disappear through algebra. And this answer, you see, it's still Gaussian function, minus x squared, and in the denominator we have sigma naught plus. So because we were multiplying wave function by its conjugation, first, we got rid of imaginary unit. Second, we got time not linear but squared. And this is what is ready for interpretation. Squared real. So if we take the thing from this denominator, so we can draw this function. It will be very sharp at the beginning, and as time passes by, it will be more shallower and shallower. And the stuff here, which we can call as sigma of t, is here. So sigma naught plus h bar squared over m squared times t squared. So it will be ramping, becoming fatter and fatter with increasing width. Oh, I was already drawing it. So it starts initially and then goes quadratically. Okay. And if we extract the width in the momentum space, it is just it is just a constant. So you multiply this initial width and time incrementing thing by a constant, but overall dependence becomes the same. But what is important that in our considerations, we do not have inverse travel in the time, right? In other areas of science, one can include this process, but right now our time goes only forward, which means product of uncertainties will always grow, which means it will never get smaller than this threshold, which means the stuff that you have already recorded by your own words, so that we cannot precisely measure both position and momentum with arbitrary probability. If you know momentum, you do not know position. If you know position, you don't know momentum. This is called uncertainty relation. This is end of the meeting. Everyone is free to depart or disconnect, and I'll stay here and answer any questions. Next meeting is Wednesday, 11 a.m. If you haven't submitted homework or you want to appeal for mitigation and improvement, you can still try your chances and have a nice and productive 2 days until we see each other again.
Thank you.
Thank you.